So somehow this field has the full range from rather mathematical analysis of the formalism of quantum mechanics and what it can lead to very concrete materials, devices, applications that are really useful for all kinds of things.
The stage at which this field is that it's not that you have some existing layout and you just tweak some parameters. You really have to think about the basic concepts, and that's what we do. So we just think, how could you do this? How could you make this happen? And then these ideas, if they're worth something, they're tested in the laboratory, and so we collaborate very closely with this experimental group.
So for the topological insulators, this is how it went. So there were predictions from theory computations, and they were checked in the lab, which is always quite an amazing thing to happen.
So topological insulators, that's again one of these almost Nobel Prize winning discoveries. Who knows? They may win the Nobel Prize. We all know about metals. We all know about insulators. Metals conduct current, insulators do not conduct current. So this has been around for a century.
But things become interesting if there's a bit of a compromise. So if, for example, in semiconductors, as we know them for long, those systems hesitate between conducting currents, yes or no. That makes them very interesting. For example, you can make transistors, all kinds of electronics or photovoltaic cells because of, by exploiting this situation of almost conducting states.
Topological insulators are very funny insulators. They are both metals and insulators in different parts. In the center, they are insulators, but when it comes to the boundaries of the material, they are like metals, like copper.
You could say, okay, big deal. So it conducts along the surface. But that's actually the surface. You could say, okay, perhaps I throw some dirt on the surface and then it stops. That's typically what happens with currents. You put dirt and then it stops. But that's not possible because this current flowing along the surface is, now we have again this jargon, topologically protected.
And it's very fascinating. How can it be that the material doesn't conduct any current on the inside, but it has to conduct the current on the outside, even if you do all kinds of things to it. It has this protected current floating there. And I think it's clear enough that there will be applications where this is the perfect idea for making a smart device.
You immediately get this idea that topology is robust. That's the buzzword. If something is topologically protected, that's the word we use. If something is protected by topology, then it's robust. And robustness, that's the basic obstacle or our basic friend in trying to build a quantum computer.
We have been trying during the last years to construct a quantum computer. It's supposed to be much better than a classical computer, and it should be able to do tasks that a classical computer cannot do.
But once you think about a computer, you think about zeros and ones. That's how a computer operates. And so you can think, what happens if instead of having something which is either 0 or 1, you have some number, some object, which is 0 and 1 at the same time.
Classically, an electron can be like this. It's spinning, let's say, left around, and that's what it does. You could say it can be like that in the other manner. But now in quantum mechanics, it can be a little bit of both. So we say it's one plus the other possibility. And if you measure the system, you will find one or the other with a certain probability. That's called a superposition. Now, if you have two electrons, it's even more spectacular. You could, for example, say they can be in this situation. Number 1 is up, number 2 is down with the spin. Or it could be like this, where number 1 is down, number 2 is up, and it's the other way around. And it can be in a superposition of a bit of the first and a bit of the second possibility. And if that kind of state is happening, and you do smart things with operating on such states, you can actually do a computation, it turns out, which is different from a classical computation.
The Netherlands has been already playing an important role into that. For instance, in Delft, they have been trying to build up qubits for the so-called quantum computer. But most of the efforts relied on charge or flux qubits. And those ones, they have a problem because they are connected to the environment. So this contact to the environment makes them decohere. And that's the main problem towards the construction of a quantum computer.
Quantum computers are not robust, they're intensely fragile. So any way you can come up with making it more robust gives you a big advantage, and topology is this new ingredient.
One analogy I like is, with shoelaces. So if you take a shoelace, you can decide to make that a carrier of information, so to say. You can, for example, make the convention that if you make a lace and close the loop, you say that's my 0 of information. And if you first make a knot and then close the loop, you can say that's my 1 of information. And those are clearly different. And now there's a protection due to topology because the knot is different from the unknot topologically. And that's protected because if you take this lace and you wave it around or you wiggle it and you do all kinds of things, you never lose the knot. You can only lose the knot if you do something very drastic, if you cut the loop and undo the knot and then close it again. But short of that, you never lose it and it's protected by topology. So in the same way, you can actually have some kind of knots or twists on the inside of electron systems, such that the state with the twist is your 1 of information, and without the twist is your 0 of information. And then that's two distinct information states, which are really protected from decaying one into the other because of this topology. Yeah, so it turns out the magic of the quantum systems, you would think, if you think about it in the first place, that you lose accuracy if you do it the quantum mechanical way, because if you measure, there's a certain chance of finding this answer or that answer, so that seems like a lousy computer that would never work. But now it turns out if you exploit this weirdness of quantum mechanics, this entanglement and this superposition in a smart way, a really smart way, you can actually do computations that are better and faster than what you can ever do on a classical computer.
So there are weird things happening in that world where we don't have intuition. You could say it's down the rabbit hole, it's a new world.
The fascination is that you have a certain intuition for the world around you. For example, there's always friction, currents can never flow without resistance. All these things you have a good intuition for, and then you know that because of quantum mechanics, sometimes it's really different on the microscopic scale. So there are superconductors who don't have any friction for currents. And there's other phenomena that you wouldn't expect, but that can exist because of the quantum mechanical rules of nature.
I would say that what keeps me moving is the fact that nature is always surprising, has surprises for us.